This is the small video to show what we did in a lab about AC parallel circuits. It's truly amazing what we can do at TAFE in the lab with some of the basic equipment like the common breadboard and our simple trusty calculator. And today doing the lab with the parallel components in AC circuits. Let's see how it goes. Here's our lab board as we made it up. Just change the focus there and come in on the essential components. There's our two sensing resistors, there's our 0.1 microfarad capacitor, and there's our 1K resistor. Alright, this is the lab for the parallel RC circuit showing the current phase shift. Sadly, we can't show the actual total current in the circuit, which you can see here, the phase shift between the resistor current and the total current is 26.7 degrees, and I'd have 90 degrees minus theta, which would be the difference between the current in the capacitor, which is leading in this case the total current in the circuit. So a little bit difficult to do, and we can have a look why when we see this circuit. That I've used two sensing resistors and I've used channel 1 on the oscilloscope to measure in this particular circuit. However, I think I did in practical, it might have been the other way around, not quite sure now, but measuring the voltage drop across the 10 ohm resistor, which gives me the current through the capacitor, measuring the voltage drop across this resistor, which gives me the current travelling down through the 1K. And then of course, if we think about what we're looking at here, we're looking at IC and we're looking at IR. So always come back to your phasor diagram to think about what we're going to get. Here's IC, here is IR. They are 90 degrees apart, so when we get the results from this on the oscilloscope and we look at the actual phase difference between the two well, voltages, or if you like, derived currents from those voltage drops, we'll see that there is in fact exactly 90 degrees of phase difference, indicating there that we've got a phase lag with the resistive current compared to the capacitive current in the circuit. And here's just some calculations that I've done using the 800 Hertz to calculate IC at 1.42 milliamps, calculate IR at 2.82 milliamps. And there's just the maths there, using the polar function on the calculator to take those Cartesian coordinates and put them into something a little bit easier to work with. Then using arctan of IC on R to get the 26.7 degrees, all done with currents of course, because voltage is the reference here. Well, I shouldn't say reference, voltage here is common between all of the elements because it's a parallel circuit. Okay, that'll do. Let's go on and have a look at the oscilloscope waveforms. When you're doing this laboratory with a parallel RC phase shift setup, you're probably going to encounter some weird geometry happening on the screen because of the triggering and because we're using such high sensitivity on the input channels of the oscilloscope. So where I've got the trigger set at the moment for edge triggered off channel 1 on the trigger menu, I'll go into setup. And then I don't want DC coupling because there's a lot of extraneous electrical noise in the classroom that I want to get rid of. So I'll hit that DC coupling, I'll come down to HF reject. And you can see there now it's as stable as we're going to get it. There's still a little bit of fuzziness in the waveforms, but that can't be helped because, like I say, we are using very high sensitivity on the oscilloscope, and it's just picking up a little bit of extra AC noise. But nevertheless, the oscilloscope is telling me that I've got 15.7 millivolts RMS on channel 2 and 24.2 millivolts RMS on channel 1. So just reviewing what we were doing, here's the circuit with the 8 volts peak to peak, which is 2.82 volts RMS at 800 Hertz. I should have written that down there. Coming into our circuit, we've got parallel branches here, one with 0.1 microfarad, one with 1K. We wanted to measure the currents coming down through each branch, and we've put 10 ohm sensing resistors in the circuit, and then channel 1, I think, is measuring the resistor, well, current by measuring the voltage drop across that resistor, and channel 2 is measuring the capacitor current. And then we looked at the phase difference between the two channels, channel 1 and channel 2, and we put cursors on each waveform, came up with 312 microseconds, which we divided by 1.25 milliseconds, which is the period at 800 Hertz, multiplied that by 360 degrees, and that gave me exactly, well, I'm going to call that 90 degrees. And that's what we should get, because if we look at the phasor diagram there, we've got IC, we've got IR, and IT would be the vectorial addition of these two, and that was originally mapped at 26.7 degrees. Sadly, we can't see that on the oscilloscope because there's no way with grounded equipment, commonly grounded equipment, that I can measure one of these branch currents and then measure the total current, because to measure the total current I'd have to put this point to this point, then have one sensing resistor to measure that total current. And I can't split the channels because of the common earth on the oscilloscope. So that's a bit of a bummer, but we'll just live with that. Looking at the currents, we had the original calculation. We got 1.42 milliamps for IC. We measured 1.5 milliamps for IC. We calculated 2.82 milliamps for IR, and we got in the measurements 2.41 milliamps, which is pretty close to the mark. And IT, look, I might set it up to do IT. We should be getting the vectorial sum of those two, which is 3.16. And again, sadly, we can't look at the waveforms to see our phase angle here. If we had some floating test equipment, it'd be a bit easier, but with the commonly grounded equipment, we just cannot do that with our parallel circuit. There's just a nice shot of the Rigol oscilloscope that we use in all of our labs here at TAFE New South Wales, Mount Druitt. I've just rewired the breadboard now, and I've only got one sensing resistor, so I've got my capacitor and my 1K resistor connected with this black wire so that they are now in parallel, and only the one sensing resistor, which I'm using on the oscilloscope, to see the voltage drop across that, which relates to the current for the circuit. We approximated that we calculated that the total current should be 3.16 milliamps. Let's see what we get on the oscilloscope. As I did say before, sadly I can't show the phase difference between the total current and IR or IC, because it's just unwieldy to do that with commonly grounded equipment. But here's the total current in the circuit being sensed through the 110 ohm resistor, and you can see here I've got 29.2 millivolts, which should equate to 2.9 milliamps RMS. And in the theory we've got 3.16 milliamps RMS, so I'm very happy with that result, which is the vectorial addition, of course, of IC and IR. This is the small video to show what we did in a lab about AC parallel circuits.